So our volumes, if I was to get some random curve, there it is, y equals function x. So when we were doing area, we split it up into individual rectangles. If I was to rotate that individual rectangle, or slice, I would end up with, well, a disc, if you like, some sort of cylinder. We know the radius of the cylinder would be whatever the y value is, and the height would be, well, whatever the change in the x value is. We know the area of the circular face would be pi times the radius squared. So pi times whatever function x squared is. Which means my slice, now I've called it delta v because it's the change in the volume, because as we go along in our shape, each slice would have a different volume, so it'll be changing as we go along. But it would be pi times our function squared times whatever the thickness is, delta x. Now, if I was to add up all of these rectangles, I would get the whole shape. And so that's what I'm saying there. If I was to sum up all of these rectangles going from A to B, I would get my shape. It would be exact when that thickness was getting very, very close to zero. Well, we've already seen what happens if, forget about the pi being there, because I can always factorise that out. But you'll recall that when we did area, if we had something like this where we added up all these functions times the thickness, well, we said, oh, well, that was the area under the curve. And the area turned out to be the integral. So it's the exact same thing. It's still the area, but under this function x squared curve, but times pi, because I've factorised the pi out. So we end up with this little formula, pi times the integral of a to b of function x squared dx. So here's another random shape. Go from a to b, whee, rotate it around, and we get some sort of odd shape there. One of those things, what do they call them? Vases, whatever you want to call them. You know, they put the flowers in. If we want to find the volume of a solid that we're rotating around an axis, if I'm going around the x-axis, a nice simple way of writing the formula down is to go, well, it's pi times the integral of y squared dx, y of course being the radius. And if I'm going around the y-axis, it would be pi times the integral of x squared dy. And how do we remember this one? Well, if we're going around the x-axis, it's dx. And if I'm going around the y-axis, it's dy. So let's prove some shapes. Like you accepted blindly the formulas for volume of a cone, for instance, but now we can prove it. If I was to rotate a straight line that goes through the origin, so y equals mx, m being the slope of the line, of course, and I'll go from 0 to h, because that'll end up being the height of the cone, rotate that round, and we get a cone. There's a picture I came up with, might be a bit more. You like that one? Do that one. So we rotate it, we get a cone. So volume pi times the integral of y squared dx. The reality is I probably don't write that first line in because I don't like seeing y's and x's in the same integral. So pi times the integral of m squared x squared dx, going from 0 to h. Well, m squared is just a constant, so I can factorise that out. Add 1 to the power over the power. We get a third x cubed, going from 0 to h. Sub it in, and there's our formula for a cone. 1/3 pi m squared h cubed. Now, you might be thinking, hang on, that's not what I recognise to be the formula for a cone. And that's because we don't normally write the formula in terms of the slope of the cone. So let's turn it into what we're used to seeing. Well, remember back over here, it was the slope of this line. Let's call that height r, the radius of the cone. So therefore the slope would be rise over run, so r over h. Let's sub it in for the slope, and there you go. We get what we're used to seeing, 1/3 pi r squared h for the cone. Let's do the sphere. Again, another formula which before now you just blindly accepted, oh yes, this is the formula for a sphere. So if I was to rotate a circle, or indeed I really only need to rotate the semicircle, I suppose, I don't need to rotate the whole circle, we'd get our sphere. Voila. Okay, so pi times the integral of y squared dx. Well, my formula already has y squared in it. Rearrange that, I'll get r squared minus x squared. And I notice I've gone 2 pi. I've taken advantage of symmetry here instead of going from minus r to r, I said twice 0 to r. So we get r squared x minus a third x cubed. Substitute in r, substitute in 0, and this one comes out straight away. There is 4/3 pi r cubed, our volume of a sphere. Just like area, if you know what the shape's going to be, use the formula that you already know. So if it is a question where they're rotating a semicircle or something like that, you go, oh, well, I know this is going to be a sphere, so I'll just use the formula for a sphere rather than doing the integration. Let's do this one. We have a parabola, and we're going to rotate about the y-axis between 0 and 1. We don't have a formula for that. We will end up with a shape known as a dome. That's interesting. Whoop, there it is, by the way. Look at that. The shape is known as a paraboloid. This time I'm going around the y-axis. So it's x squared to y. X squared is y. So we're going to integrate y to y. Now, add 1 to the power over the power. And we get y squared on 2. Substitute in 1. Substitute in 0. And there's our volume. Pi on 2 units cubed. This shaded region here we want to find the volume of. Now, careful, bit of an optical illusion. The eyes can play tricks with you here. But so basically what we've got is a cylinder with a cone that's sort of been drilled out of it. But if you look at that, it can pop in and out at you. But what it actually is there's a cylinder with a cone has been taken out. We've got 2 and we're subtracting. You square them before you subtract because you're saying it's the volume of this shape minus the volume of the second shape. So you find the volumes first before you subtract. So if I'm rotating around the x-axis, the top boundary is just the line y equals 5. So that's 5 squared. The bottom boundary is y equals 5x. So I'm going to take away 5x squared. So I'll end up integrating 25 minus 25x squared. I can factorise out the 25, sub in the 1, sub in the 0, 50 pi on 3. Of course, with that one, remember what I just said? If you recognise the shape, as I said, we have got a cylinder and we're taking away a cone. So it's pi r squared minus a third pi r squared. 2/3 pi r squared. Sub in the radius, sub in the height, bang, you get the answer straight away. HSC question. We've got 2 parabolas, one concave up, one concave down, and we're going to rotate that one. First of all, they asked to find the points of intersection. So we'll solve x squared equals 12 minus 2x squared. We get x equals plus or minus 2, so they meet at 2, 4. Now, technically, I've got that wrong. The reason I wrote down 2, 4 is because I looked at the shaded area and just said, oh, it's 2, 4. But the question does say points of intersection, so I really should have put down minus 2, 4 as well, because it does have 2 points of intersection there. Now, they've given us a bit of a hint on how to solve it. The shaded region between the 2 curves and the y-axis is rotated about the y-axis by splitting the shaded region into 2 parts. Find the volume. So there's the picture again. We're going around the y-axis. Remember, you've got to look at your boundaries. Top boundary minus bottom boundary. So if we go into the y-axis, well, the bottom boundary is consistent. It's the y-axis. But the top boundary changes. I've got the concave down parabola and the concave up parabola. So they're the 2 bits. You'll end up with a rather interesting shape there. If you can see, it's the solid bit in the middle, of course. An Easter egg, maybe. Maybe that's what that is. Although it's a bit sharp at the sides, I think, but it sort of looks a bit like one. Okay, so we're going around the y-axis. Split it up into 2 sections. So the top one, remember I want x squared as the subject. That's fine, y equals x squared. That's already fine. The other one would end up being x squared is 6 minus a half y. So I want to go 0 to 4 of the bottom one. So y to y. And then 4 to 12 of the top one. And that's our 6 minus a half y to y. Integrate both of those. Notice I changed this positive to a negative, which you might think is an odd thing to do. But the reason I've done it is now I've got 4 on the top of both. So when I substitute in, I know I'm just substituting 4 into all of this. And so I go 4 squared on 2, then minus 6 times 4, minus will be a plus. But then I'm going to take away the 0 for the first one, so 0 squared on 2, and then take away, although minus will be plus, the 12 for the second one. That's just to save a little bit of time. It doesn't save that much time. We end up with 24 pi as the answer for that one. Cubed units, volume. Cubed, that's honestly, that's a 3. Okay.